Hello, everyone. Thank you so much for joining us today for the first in GenZ series of heterogeneous computing webinars. Today, we're going to be talking about laying the foundation, GenZ components for heterogeneous computer networking. We will get started in about 2 minutes. We're going to give folks a little bit more time to join. So please settle in, and we'll be right back with you. Hello, everyone. Thank you so much for joining today's webinar from GenZ. This is the first in our series for heterogeneous computing. Topic today is laying the foundation, GenZ components for heterogeneous computer networking. Today's presentation is going to be provided by Matt Burns from Samtec and Tim Symons from Microchip. We will have a live Q&A session at the end of the presentation. So please submit your questions through the question feature on the right side of your screen. And at this point, we'll pass it off so that the presenters can kick off the presentation. Thank you.
Thanks, Rachel. This is Matt from Samtec. Tim and I are very excited to be with all of our attendees today. Just a brief overview of what we're going to discuss over the next hour or so. Tim's going to get our presentation started by looking at what heterogeneous computing is and some of the benefits that GenZ brings to that. And then we're going to lay literally a foundation of showing the readily available components from within the GenZ membership that help to create heterogeneous computing solutions. So we'll talk about GenZ Scalable connectors, we'll talk about the GenZ PECKFF infrastructure, we'll talk about readily available IP and silicon solutions, memory modules, how we tie that all together with the recently released GenZ Development Kit. We'll have some key takeaways in our summary, and then as Rachel said, we'll open up the Q&A for the audience. So with that, we're going to turn it over to Tim. And he's going to talk about the benefits of GenZ for heterogeneous computing. Tim?
Yeah, thank you, Matt. So, yeah, again, this is Tim Symons from Microchip, and I'll start with an introduction of, for those who aren't that familiar with GenZ, GenZ is a memory-centric fabric, and we have a conceptual diagram here on the right. So there's a transition ongoing to allow executable memory to be attached to CPUs, GPUs, and expanded. So this would include DRAM, and then new types of memory, such as storage class memory, and also extends to peripherals. So in this environment, you can see that it's an address-based environment. It can have shared different processor types, GPUs, FPGAs, accelerators, and then at the core, essentially you can put memory and data at the core of your processing system, and this is where it really gels well with grid computing, heterogeneous computing, such that data can be stored in a centralized database in executable memory space. Then processing engines can be allocated to do tasks against that pool of memory without having to move it. So that's one of the usage models. There are many that can be executed with this architecture. But essentially how this relates to heterogeneous and grid computing is that by centralizing the data, not having to move it from a storage location into executed memory space where it can then be processed and then returned, GenZ and this transition enables that executable memory to be directly accessible by multiple processing types. So let's move to the next slide. So that was a conceptual diagram. Let's have a look at how it comes into an executable form. So in this diagram, you'll see across the top a representation of servers going through a GenZ switch, and in this diagram, we're showing it attached to different resources. So on the left, we have pooled DRAM, so that would be executable memory, cache memory, or just memory for high-speed access. Next, just below it, we see new memory types, and we see that in persistent memory, new memory technologies, so ReRAM, and other types of memristors and so on. So those memories have similar execution read-write speeds to DRAM, but they are persistent. And that adds new challenges and also new opportunities. And GenZ, again, is a fabric that enables processors to access that. As we move to the middle here, we see pooled accelerators. One of the obvious conclusions there is like, oh, GPUs, we'll offload things to GPUs, and that's commonly done in systems. But if we move down to new accelerators at the bottom right there, there are opportunities for customizable functions. They could be customer-specific functions that do filtering on data or compression or other functions that can be unique. And they could be optimized in hardware. And again, that allows each processing type to do what that processor does best. And finally, on the right, we see pooled storage. So not only GenZ talks to memory, but it can be expanded out to talk to centralized storage. And this allows, again, this concept of data in the middle, processors executing actions on that data around the periphery of the data. This saves a lot of power, cooling, and data movement, so it saves time as well. So let's move on to the next slide. So, along with this request for higher performance and memory accessible compute performance, we really need high bandwidth and low latency. If you're going to take DRAM and put it off the motherboard and attach it to processors, GenZ needs to provide a high bandwidth, low latency fabric, and that's exactly what it does, and that's why it was created. GenZ's differentiation is that it's memory semantic, so it's read, write, load, store operations, can execute on a byte level basis, and all of the devices are addressable. So they're effectively addressable. And what this means is that peers can communicate with each other relatively transparently. So in this figure here, we show in the center we have a traditional processor, and to the right, top right, we show DRAM ports on there, and the access speeds for those are somewhere around mid 20 gigabytes per second. Add-in cards on the left would be on the PCI bus, and then what GenZ has to do in the orange lines at the bottom, we want pooled memory and pooled accelerators. And what GenZ does is runs that at 200 gigabytes a second, depending on the lane width, of course. But it's designed for medium to long reach, so it can go from inches to yards. So it allows rack-to-rack communication of your actual memory and data. So with that, GenZ Consortium has had to design high-performance connectors, robust connectivity, new form factors for the accelerator functions such that they can be plugged in and added to the infrastructure. And then the switching and the pool of resources can be allocated by a fabric manager and controlled so that data can either be segregated and protected from other processing engines or shared and grouped together, depending on the application requirements. So with that, let's hand over, and Matt, let's have a look at the actual devices and performance connectors and functions we have.
Great, Tim. And you make a nice point that shows the necessity of redefining the electromechanical interface for GenZ, right? When GenZ started their efforts a few years ago, looking at across the solutions that were available, there were limited options, or maybe not even any options that provided a pathway, leveraging existing electromechanical and electrical infrastructure, but providing a pathway to 112 gigabits per second PAM4 operation at the channel level. So that's really where the GenZ Scalable connector came in. The GenZ Consortium worked together to create a new interconnect specification, which eventually was handed over to SNIA, which is now defined by the protocol SFF TA1002. This standard that GenZ developed covers mechanical and electrical performance of the interconnect, while the various form factors that utilize the SFF TA1002 interface specify the pinouts. So, the versatility of the GenZ scalable connector, as well as the performance, has made it an attractive solution for a number of applications, whether that's OCP, NICs, high-speed cabling, NVMe, native NVMe of drives, EDSF for storage, which we'll talk about later in this presentation, as well as PECKFF. The GenZ scalable connectors, like similar card edge connectors, come in a number of variations: 1C, 2C, 4C, 4C plus. They are mechanically interoperable. So that provides for scalability and flexibility when it comes to electromechanical system design. A number of applications are designed in terms of being vertical, right angle, orthogonal, straddle mount, cable configurations supported. One of the other key goals that GenZ created was to leverage and take advantage of legacy protocol physical layers. So PCIe 802.3 those are supported in this GenZ scalable connector, and the optimizations that GenZ offers in terms of lower latency and increased throughput is one of the direct results of that is the optimized interconnect that was defined by GenZ. One of the biggest differences GenZ adopted versus some of the other card edge connectors available on the market is going from a 1 millimeter pitch down to a 0.6 millimeter pitch interconnect. So what that allows for is optimized SI performance and also enabling FEC-free low latency ecosystem. It allows for multiple connectors per module. And also a variety of flexibility and scalability within the ecosystem. Moving to our next slide, this just illustrates some of the everyday applications that the GenZ scalable connector enables. So, looking at the illustrations on the right-hand side, you can see that there's memory modules can be supported by the GenZ scalable connector, cable-to-cable applications. There's a roadmap for optical solutions, obviously with the EDO conversion, and then you can see the various sizes that are available there as well. So adding cards, hot pluggable modules, electrical cables, optical transceivers, forward and backward interoperability. The cards are protocol agnostic, so it enables a common connector to support a number of applications that are illustrated here on the slide. It also enables having a solution of the interconnect solutions available from multiple vendors. So it simplifies the BOM costs within a system, increases volume, and reduces overall costs for the OEM community. And the other added benefit that we've talked about in previous webinars around the GenZ Scalable connector is that it supports PCIe 5.0, 100 gigabit Ethernet, and provides a pathway to 112 gigabit per second PAM4 channel performance. In addition to the GenZ Scalable connector, GenZ has also expanded the electromechanical infrastructure to support heterogeneous computing in all its form factors. So GenZ has developed the PECKFF, or the PCIe enclosure compatible form factor. Many listeners may be hearing this for the first time, or hearing this term for the first time. So just at a high level, what is PECKFF? It enables mechanically compatible add-in cards that are very similar to PCI Express Chem AICs. It uses the same latching features. A lot of the physical sizes are the difference. As we mentioned earlier, it complies to the SFFTA 1002, so it provides for increased density and increased performance. Another advantage that PECKFF uses, and the GenZ Consortium was very strategic in wanting to support, is the 48-volt ecosystem that's common in data centers. Not only does that allow for high power, up to 600 watts per AIC, but it does lower operating costs over the long run of the equipment. PECKFF has been designed to support any component type, the various card sizes, card lengths, half length, three-quarter length, full length, double width, allows for supporting memory, CPUs, server applications, GPUs, FPGA-based acceleration cards, AI and machine learning applications, and similar. Another advantage that we've seen coming out of the GPU arena or the AI arena is top card connectivity. So the GenZ PECKFF supports AIC top edge connectivity with AIC to AIC cabling options. There's flexibility in terms of thermal mitigation, both with that being supported actively and passively. We talked earlier about the SI performance of the connector. There's also been design focus on the PECKFF cards, moving the edge cards 60 millimeters closer to the processor, which shortens trace lengths, reduces the need for retimers from an SI standpoint, and eliminates or minimizes the need for exotic PCB materials, which adds burden cost to OEMs in this space. So these, among any number of other factors, promotes improved SI or allows for improved SI performance, as well as routing up to 64 high-speed differential pairs between the PECKFF cards and the motherboards that they plug into. This illustration on the right really helps to illustrate how PECKFF allows for leveraging the advantages of heterogeneous computing. Not only low latency and high performance, but also supporting a variety of standard compute engines. It also shows that a PECKFF chassis can theoretically support a mix of PECKFF and PCIe Chem AIC solutions. Whether that's a server-based application in a PCI Express Chem AIC solution, or an acceleration platform, an AI acceleration platform, or FPGA acceleration platform using different compute engines. You can see the card-to-card connectivity, adding NICs, whether that's using a PCIe or a GenZ fabric. PECKFF, again, was really designed and really intended to leverage the benefits of disaggregated infrastructure for heterogeneous computing networks. Now, someone may ask, how do we know that PECKFF works as advertised? Well, one of the case studies that Samtec and several of the members of the GenZ Consortium worked on is what we affectionately call the PECKFF emulation platform. So this is a chassis at the card level that gives silicon vendors, system designers, basically anyone that wants to show that GenZ works as performed, a test platform to look at signal rates across a number of configurable and flexible architectures that uses the PECKFF infrastructure. This particular platform can support by 2 interconnects with reflection and crosstalk sources. It supports common topologies. If you want to look at signal performance from one AIC to the backplane, or connecting between 2 adding cards across the backplane, or looking at top card connectivity, those signal traces and those signal routes can be designed and implemented and tested to verify performance. The rest of the system is outfitted with high precision RF interconnections. The cables can be adjusted to any length or manufacturing any length to test whatever configuration a user may come up with. The PCBs support 85 ohm impedance, and the cables are flexible enough to support 85 or 100 ohm impedance. Moving to the next slide, this is an actual picture of some of the test results that we received or that we've observed testing this platform. Looking at the data on the right-hand side, the top 2 lines show the signaling, going AIC to AIC, and then the bottom 2 lines show top card connectivity. So the results, just using some PBRS31 data from a transceiver source, external transceiver source, shows eye heights, roughly around 200 millivolts, bit error rates across the entire channel around 3e to the 14, and you can see the total number of bits. For those that are interested in getting more information on this test platform, there's other webinars that the GenZ Consortium has put on that delve into the details of this platform in more detail. So, Tim, we've talked so far about the interconnect and some of the electromechanical infrastructure that's available to enable heterogeneous computing using GenZ tech. What are some of the IP and silicon solutions that are available to round out the system design?
Yeah, let's have a look at some of the options available today here. So, this first view. Firstly, GenZ is a protocol, memory-centric protocol, and so implementations will require the PHY and the protocol layer. This is a diagram by a vendor, PLDA, who do IP cores. And just really showing that they've integrated a switch core into this particular example. Then you have on the left-hand side your protocol controller, which talks GenZ and creates the flit structures and the transport layer with the error correction and so on to ensure that we can go long distances at high speeds. This is part of the IP. And then on top of here, we see a request to responder interface that would then be used to connect to your own accelerators or processors as required. In fact, if we have a look at the next slide. Next slide.
Sorry, Tim. Sorry about
that. It's okay. So this was a demo we showed a supercompute, and this exact IP that I just spoke about was instigated onto 2 identical boards with ARM CPUs, and then the blue cable in the middle, that's fiber optic. So optical cable was used to interconnect between the 2 processors, and they were sharing memory seamlessly between the 2. So sometimes a processor was accessing memory on the other platform, and sometimes accessing it locally, and really the application couldn't see the difference. So one example of implementation there. Next slide, please. So if you have a look, here is an example of design and development platforms by IntelliProp. and this IP shows a memory controller. So you'll see on the top here we have multiple channels with DRAM support, and then the IP will do all the memory controller and management of that memory, and then represent it out to the bottom of the device here, and they're showing 4 ports, each of 4 lanes at 25 gig in this example. And so the full memory controller here is supported in this particular design. Let's have a look at the next one. The next one, and there we go. And so here's another one. IntelliProper put together a processor bridge function. So here we see at the bottom we've got two GenZ ports. And then if you see the transition from the burgundy colored, which is the IntelliProper IP and specific GenZ functions, the transition or intersect point there is the AXI bus, and they're using that to talk to, in this case, 4 ARM A53 processors. And this design has been used in some of the development kits and is available in there as well. So we'll talk about that shortly. Let's have a look at the next slide. So when we put this together in the GenZ environment, you may have noticed that both of the IP vendors included switches within the function. And so if we look at the diagram on the right here, we have ARM SoC. That could have been one of those functions there. And that's feeding sideways to the blue box, or GPU accelerator, or or whatever you want it to be actually. And then so there's an interconnect directly between those two, so they can communicate directly with each other as peers. And then you'll see from both the ARM and the GPU, they have a connection going down to the green back, almost like a backplane environment, connected to memory. So the representation here is ZMM, that's GenZ memory module. And so the representation would be almost like an SSD, but the examples we have today I use DRAM. You plug in your DRAM module, and then you can either allocate the entire resource, the entire function of the SSD, to one of the processors if they require that much memory for their application, or what's shown here in the diagram, the actual ZMM module has been partitioned such that it has 3 orange blocks that are dedicated memory areas to the ARM SoC, and in this case 1 blue block that has also been allocated to the GPU. And these will be private areas. They're not sharing the information, this data, as far as the GPU and the ARM processor is concerned. They're separate memory, physically separate. They're not aware that they're running through or sharing one memory module. At the very bottom here, we show both blue and orange in little stripes, and this is a representation of shared memory. So let's say there's a database that both processors need to execute a function, you referencing that data. So you can allocate sections to sharing, and so both processors have equal access to this memory. It's much easier to think of as a read-only area. However, they can be write and read, such that the processors can hand data backwards and forwards to each other. But this is an example of both that IP that we've seen earlier in operation, the interconnects and the cables, and the pluggable modules there. And this really hints to our title topic of heterogeneous processing. These processors can be of any type. There's no reason why there can't be an x86 processor here, ARM, NVIDIA GPUs, and custom accelerators, all sharing the same database in the same fabric. I guess one thing to add there, sorry, just one more.
Sorry, Tim.
No, that's fine. I hesitated. Coordination and allocation of the resources is done by a fabric manager, And so a fabric manager will allocate resources, and there was a great webinar recently about how that is being developed using for Linux and other operating systems to ensure that the systems can be configured and safe. Okay, now let's hand over. Yeah.
All right. Sorry, I was so excited to talk about GenZ memory modules. We got ahead of ourselves. But Tim illustrates some nice points in that last slide and in that last section about some of the advantages that GenZ brings for heterogeneous computing applications. And one of that is, the availability of scalable and flexible memory system architectures, right? If you think about motherboard design, space is limited. So there's ongoing efforts to get memory outside the box and leverage fabric technologies. Obviously, this isn't a new technique, but there's always faster, more efficient, lower latency paradigms to follow to optimize the network. So that's where GenZ adds some nice benefits versus some of the other solutions that may be available right now. Just as a setup to show how GenZ has thought ahead to really try to enable paradigm shifting memory infrastructures is really the development of the GenZ form factor for memory modules, or ZSFF. The mechanical working group within GenZ took a market snapshot, if you will, to understand what was common form factors across the market, and then how could we leverage those in combination with the work that was being done around the GenZ Scalable connector, the SFF TA1002. And what quickly came to the fore was a new module size, what we're calling the media modules down here on the left-hand side, that coincide with the EDSFF 3-inch form factor that was derived from the GenZ developed ZFF. These fit in 2U and 4U servers. They can support a number of memory module densities. They can support a number of memory types, whether that's flash, SCM, DRAM, or other memory types to really support disaggregated architectures that are common within heterogeneous computing applications. So an example that Tim alluded to in his previous presentation are that there are ZMMs or GenZ memory modules available right now. GenZ member Smart Modular introduced their GenZ memory modules within the last few years, high density solutions that are standard to the EDSFF E3.S form factor. They leverage the 4C configuration of the GenZ Scalable connector, which supports up to 16 lanes of GenZ. Their particular GenZ DRAM modules support 64 gigabyte or 256 gigabyte capacities. There's support for dual DDR at 2400 data rates. These GenZ memory modules have been used for both programming, prototyping, and production. Tim earlier mentioned the memory modules that are available from GenZ member IntelliProp. This is one of the first applications on the market where Smart Modular worked with IntelliProp to use the memory controller, or the Mamba controller, within this particular platform. These GenZ memory modules also can be used in in-memory analysis, similarity search, large-scale graph inference, financial modeling, and other applications. So, we've talked so far in this presentation about a lot of bits and pieces, a lot of components, a lot of solutions that are available right now, but how do these all tie together? GenZ was really excited to release the Micro Development Kit in 2020, And we just wanted to spend a few moments. Tim's going to just give a few brief details of what's in the Micro Developers Kit and how it ties it together, all the pieces we've talked about so far. Tim?
Yeah, thank you, Matt. Great intro. So, yeah, what we've done last year, the consortium members, GenZ is a consortium, so we have a huge number of companies contributing concepts and ideas. And one part of that's tough to develop is operating systems, drivers, and management software. And now that's fully defined in specification form. We need an example platform, and so the Micro Development Kit has been developed, and this allows the software infrastructure to really become established. It's I'll show an exploded view next, but in this diagram here we see it's sort of it's like an orange plastic box. What you've got on the left-hand side are two cooling fans, and those are like parking bays for memory modules. So that's your memory resources. And then you'll see on the right-hand side of the orange box we have PCI add-in cards. And so this allows you to run your processors. You can run one or two cards, and those can communicate with each other, with the memory, sharing the memory, and can really exercise the GenZ infrastructure in quite a small, compact environment. So this has been, this was launched last year and is available for development, and we're starting to see the fruits of that through Linux environments and developments that are ongoing right now to support GenZ and really to make the memory semantic direct processor to external memory access be more and more robust and more bring it to life. So if we have a look at the next slide for a second. Yeah, Matt, next slide. Yeah, thanks. Yeah, so this is just an exploded view of that same chassis. So we go from left to right. So this cooling fans, obviously, we're talking DRAM memory and very high capacities of it. Each of the ZMMs are 96 gig of DRAM, and you can run 4 of them. Up to 4, I guess, in the chassis. In the bottom left, we see that this is the Smart Modular IntelliProp ZMM module that you can plug into that backplane. Then moving across, we see the two PCI add-in cards, and to the right of that, an example of that add-in card is, and the reference design is from Bitware. That's a Molex company, and that uses FPGAs on it. And you'll see the Xilinx programmer in the middle there. That's because, okay, you put the GenZ IP, that's your interface, but you want to add your differentiated product behind that, be that a memory controller, processing engine, accelerator. And so that's exactly what this development kit is designed to do. So you focus on your value add while you use the IP to interface the external memory and take advantage of the pooling or external resources as and when required. You'll notice at the top right there is that your external cable as well. These boxes can be linked to external systems. You could have multiple of them linked together. And hopefully at demos, if we have physical demos this year coming up, then you'll see this box in action. But anyway, that's looking ahead. So yeah, the development kit is here. Let me pass back to you, Matt. Next slide.
Sorry, Tim, I was talking on mute. Just wanted to add one other point here about the Micro Developers Kit. One of the things that I think that's really unique about this solution that the GenZ Consortium has come up with is that this ready-to-use, easy-to-use Developers Kit can be used in a variety of use cases, right? If there's hardware designers out there that are looking for proof of concept to test their solutions versus what's available already, obviously it allows for software development, whether that's at the firmware level or the IP level for a number of solutions, and then really at the top level, application developers can use this to test their solutions on a ready-made reference design that leverages all the benefits of really a GenZ heterogeneous computing application. So I know you're excited. I'm excited about. We're all excited about seeing how the GenZ Micro Developers Kit, really helps GenZ, kind of take that next step, if you will. So as Tim mentioned, just want to wrap up a couple key points of the webinar from today. As Tim mentioned earlier, GenZ is defining memory-centric ecosystem that really enables disaggregation, distributed computing, resource pooling, acceleration, and offload. Resources that we've talked about include the Micro Developers Kit for developing applications that leverage the large-scale memory platforms made possible by GenZ. And we've also talked a lot about a number of the components that go into the ecosystem as a whole, the scalable connectors, the PECKFF form factors, pluggable and upgradable modules, whether that's accelerators, the memory modules themselves. We didn't talk about it in this webinar, but there are protocol testers available to handle GenZ development from that standpoint. And one of the key takeaways, obviously, is that GenZ is an open and accessible protocol that leverages the strength of the entire consortium. In line with that, GenZ has been around for a number of years as an open source standards community with broad industry support. We're not going to read all the names here, but we have over 60 members that continue to contribute to the GenZ Consortium, not only developing the standards, but also adopting and pushing forth solutions around GenZ technology. And if anyone's listening is new to GenZ, we welcome you to join us in our efforts. So if you'd like to learn more about membership or the GenZ Consortium itself, or if you'd like to dip your toe before diving in head first, would love for you to sign up to receive our newsletter to keep up to date with everything that we're working on. Please visit our website, genzconsortium.org. We also welcome all of our attendees to keep up to date with us on social media via Twitter and LinkedIn at the GenZ Consortium. Rachel, I think that's going to bring our webinar to a close, but let's turn it over to you for the Q&A.
Great. Yeah, we do have a few questions that have come through. We can continue taking questions for now as well. But to kind of kick things off, the first question that we have is, can GenZ support protected zones so that data is private for each processor?
Yeah, I'll take that one. So yes, is an easy answer. Let's explain a little more about that. So I think in one of the slides I showed an example of a memory module that was connected to the GenZ fabric. And when a memory module reports that it can be partitioned, the fabric manager it's kind of the coordinates and reallocates resources as required. So the concept is the fabric manager gets requests from hosts saying, I need more memory. What memory have you got for me? And the fabric manager allocates that memory. And of course, a very important thing is that if you happen to be sharing a device, you don't want memory data corruption or being accessed by the wrong device. Obviously, that would have catastrophic effects, not only in terms of the operation, but also security-wise. So yes, memory partitions are allocated on a memory address range, and when that zone is created, the host can only see the memory is allocated to it. It is not aware or has no access to memory beyond that region. So the fabric manager sees everything. The host only sees what it's been given to see, and it can deallocate as well if it no longer needs those resources.
Great. Next question is, how many devices can be connected to a GenZ fabric?
Yeah, that's a good question. Yeah, go ahead, Matt.
Sorry.
It's a lot.
No, I was going to defer to you, Tim, because I forget that number.
Yeah, I think
no pressure.
No, everything's addressable, so it's limited by address range. However, there's no actual limit on the number of domains and zones you can have, and so it's in the thousands of devices. You know, in reality, your address range is limited for the zone, but the balancing act, what really comes in here is GenZ is a memory fabric. You're talking to processes in an executable memory space, and so there comes a point where you go through a switch, you go through another switch, to get so much access to so many devices that your latency becomes too long, and there's better ways of executing. So although you can put together thousands of elements, your fabric can consist of thousands of elements, but you always must balance how you configure and allow access with the bandwidth and the latency of the system. So I guess I'm hedging a little bit on the answer. It's so in the thousands, but in reality, you probably keep it down to less than 100, just because of the access and latency requirements of high-speed memory.
Okay. We have a couple more questions. The next one is, are there any opportunities for university researchers to get those micro development kits?
Matt, do you want to take that?
I honestly don't know the answer, Tim. I apologize. I don't know the answer to that one.
Yeah, the GenZ Consortium effectively is centralizing those, and they're accessible through the GenZ Consortium programs. There is obviously a cost associated to them, but yes, they are accessible, and we certainly encourage university programs. This would be a really great way to step into the world of the memory attached fabrics. This is a transition that's ongoing right now, and really brings together new architectures. So it would be a great platform. So yeah, they're available. I think the contact point would be through email to the GenZ Consortium, and then we can provide you with more information.
Yeah, to add to that, another option would be to visit the GenZ website, genzconsortium.org, and select the Contact Us feature. And if you complete that form, you can make your request, it'll come through, and someone from the team would follow up with you. It looks like we have one more question right now. It is, what is the max performance on the GenZ Scalable connectors? Well,
I know I can answer that one. Right now we're saying a theoretical limit at 112 GPM4 at a channel rate. Obviously, right now in the industry, we see a lot of PCIe 5.0 applications. We see a lot of 100 gigabit Ethernet applications. The PCI SIG obviously will be pushing forth the PCIe 6.0 application, which gives a 64 gigatransfer per second using PAM4 tech. So the GenZ Consortium members that were involved with designing the GenZ scalable connectors, have provided a pathway to support all foreseeable physical layer protocols within PCIe and Ethernet for the near term. But yeah, 112 GPM4 seems to be a workable limit for those connectors.
Okay, another question received is there a way to simulate MDC applications over GenZ, alternative to test bed emulation?
Yeah, so the best answer to that one is the consortium itself defines the specifications, and so we define the protocol. I think, as we've shown today, there are multiple vendors providing solutions into that platform, and I think the best way to respond to this request, I think at the moment, the platforms and the test beds are the physical ones that I've seen, but it's probably worth approaching some of the member groups as to whether these tools are being created there to allow that. I know the logic analyzer has an exerciser as well, but I'm not sure whether it actually simulates an entire application. So I think that's one for our consortium membership that perhaps we can take away and get an answer for you.
Great, thank you guys. I think that's all the questions for right now. If folks do have any follow-up questions, again, feel free to visit the website. You can always contact us through there, and we can get responses back to you as soon as possible or put you in touch with someone from the consortium to speak with. So with that, I suppose we will say thank you so much, Matt and Tim, for the presentation today. And we look forward to the next webinar that we will be hosting. That will be coming up in April, on April 22nd. You can follow our website, check out our events to see more information about future events. And that includes webinars, coffee chat sessions, and lots of other activities that we're involved in throughout the year. So thanks again, Matt and Tim, much appreciated. And we hope everyone has a wonderful day. Thank you.